Okay, right now we're going to review chapters 2 through 4 in Bach-Velleman-DeVoe AP Statistics, Categorical and Quantitative Data Analysis. And so first we'll start talking about categorical data. Categorical variables place an individual into a group or category. So if you have that kind of data, then you're kind of limited in the ways you can organize it and graph it. You can organize the data into a frequency table, which is a table of counts, like I had 3 red, 2 blue, so on and so forth, or a relative frequency table, which is a table of percents, like 15% red, 30% blue, so on and so forth. You can graph data in bar graphs or pie charts. To use a segmented bar or a pie chart, data must add to 100% of a total. No overlap of categories or categories that don't constitute a single whole. Now for comparing categorical variables, you can use two-way tables, also called contingency tables. If you put the totals in the table, then those total rows, which are usually the bottom row or the rightmost column, those are the marginal distributions of the variables. And it's in the margins of the table, so it's called the marginal distribution. A conditional distribution of a variable is the distribution for that variable for a specific value of the other variable. Now, for graphing things like this, you can use side-by-side segmented bar graphs, or so that you can look for an association of the variables. If the side-by-side segmented bar graphs look basically identical, then there's likely no association, or we could say that the variables are independent of each other. If the segmented bar graphs or corresponding relatively frequency graphs are not very similar, then there probably is an association between the two variables. Now let's look at an example. This is data from your textbook, but it is real data from the Titanic. First class passengers, 197 survived, 122 died. Second class, 94 survived, 167 died. Third class, 151 died, survived, 476. Sort of a contingency table or a two-way table for survival status versus class. It does not yet have any margins in the table because we have not computed, say, the total survivors. That would go right here, or the total who died, that would go right there, or the total number of people in first class would go here, second class here, third class here, and the total of all of the passengers would go down here in the right-hand corner. Okay. So our variables are ticket class and survival status. The marginal distribution for survival is 442 survived, 765 died. The conditional distribution for first class survival is 197 in first class survived, 122 died, and 319 total. Possible graph you could make, 3 segmented bars, one for each class, divided into 2 colors showing relative survival and death rates. If you do that, you would see that the 3 bars do not look nearly identical and are not all like the marginal distribution for survival. The relative frequencies of survival and death are different at a level we believe to be statistically significant. Therefore, we would conclude that there is an association between survival rate and ticket class. All right, moving on. If you have quantitative data, quantitative variables take numerical values for which taking an average would make sense. Most quantitative variables have units of measurement. So that's a good thing to check for if you're not sure if a variable is quantitative. Does it have units? If the answer is yes, it's probably quantitative. If you have quantitative variables, organize the data into a list. Make a graph of the data using a dot plot, stem and leaf plot, or a histogram, or possibly a box plot, which we'll talk about in the next set of slides. Describe the distribution using our acronym SOX: shape, outlier, center, spread. Okay, moving on to the next slide. Whoops, I think I skipped a couple slides. Let's go back. Okay, so how do you make the graphs? A dot plot, you use a number line, you label the axis, give the graph a title, and you just put a dot for every outcome on the dot plot. So if there's more than one, say say more than one person who is 60 inches tall, you might have 2 dots there if there are 2 people at 60 inches tall, so on and so forth. And so it kind of looks like a histogram when you're done, except it's made of dots. And it has every single value represented. A stem and leaf plot, Stems are usually all but the final digit. The leaf is usually the final digit. You must include a key that shows what the numbers mean. Arrange leaves from least to greatest out from the stem. Do not leave out duplicates. You may do back-to-back stem and leaf plots for comparisons. If there are many data points in each stem, you can split stems. That means you could have, say, if there's a whole bunch of values in the 20s, you could have write down the stem 2 twice and do, the 20s from 20 to 24 in one stem and 25 to 29 in another stem. If you're going to do that for all of them. Don't just split the 20s and nothing else. If they're also, don't forget a title. For histograms, divide data into bins of equal width, like 0 to less than 5, 5 to less than 10. Draw a number line with the bin boundaries. Draw bars to appropriate heights to show the counts in each bin. Label axes, no gaps between bars unless there is an empty bin. Choose bin width to have a reasonable number of bins, around 5 or so. If you have a whole bunch of bins, the graph becomes too busy. If you have too few bins, then you're likely to miss some important observations. Now, the nice thing about a dot plot is every single value is there. The nice thing about a stem and leaf plot, again, every single one is there, and you can actually see the numbers. You pretty much have to make these by hand. There are some software packages out there that might make these, but they're not that common. Histogram your calculators can make, though, and we will look at how to do that. How about right now? Okay, so if we go to our calculator, we would need to have some data in a list that we want to make a histogram for. So we go into stat, come on, go. It's not going, there we go. Stat, edit, enter. And then let's just put some numbers in there, 8, 3, 2. I'm just making up some numbers. 6.6, 4, 11, 2, -1, 9, 15, 6, 8, 7, 7.2, 5, so on and so forth. How many ever data points you want. Now when you want to go make the graph, go to second y equals. You may need to make sure, first of all, that you're under your mode, you're in function type graphing, and that your y equals menu doesn't have a bunch of stuff in there that might interfere with your graph, and that none of the other stat plots are on because they can all interfere with your graph. Okay, so you go into stat plot, turn it on, and then the third one in the first row is your histogram, and then identify the list. Now this here is if, like, let's say that you had a whole bunch of data where maybe there were 35s and 26 10s or whatever, then what you could do, instead of typing 5 36 times, you could put in L2 like how many times each number occurs. So like in L1 you would just put 5, and then in L2 you put 36, and that would be the frequency counts. Usually, however, you'll just type each number in each time instead of putting the frequencies in list 2, but you could do that if you wanted to. And then always, when you want to view a stat plot, choose zoom 9 so that the window centers around the statistical data. And hopefully, oh, I must have an equals on. It doesn't want to do that. If you're having that problem that I just had, check your apps and make sure that in equals is turned off, because sometimes that will interfere. So here's our histogram. I might want to turn this axis off later if it's annoying me. But right now, the bin widths might not make any sense. This is just kind of the default bin widths that the calculator chooses. You can go ahead and trace, and it'll tell you that it's starting the lowest bin at -1.1 and taking it up to all numbers less than 2.2. There are 3 numbers in there, so on and so forth. And you can right arrow back and forth and see what's in each bin. Having a bin width of that size, it's kind of arbitrary, so you might need to choose a bin width that makes better sense. I think we were okay with starting at -1. I think that was our lowest number. 18.2, I think our highest number was 15, so I don't know, maybe we'll try 16 for our X maximum. X scale is where you're telling it what you want the bin width to be. I'm going to try going by 2s because that makes more sense to me than 3.2. And then these numbers I might need to adjust if after I go and look at this graph, if some of the bins maybe are too tall and I can't see them in my window. Otherwise, I'm just going to leave that alone. And I'm going to hit graph instead of zoom 9. And so now I can see what my histogram looks like with bin widths that make a little more sense to me. And so we could do socks for this display. We could say, the shape, roughly unimodal, symmetric. Outliers, unusual features. Well, there is a gap in this bin here, right? There's a missing bin, so that would be worth mentioning. Center, if we're just eyeballing it, it's going to be in one of these two bins. So we could go back and look at those. We could certainly be more specific, right, than just eyeballing it. We'll talk more about that in Chapter 5. And so you should definitely be as specific as you can, but right now let's just eyeball it. And then spread, again, we can talk about the range right now pretty easily, going from, we have something in the 15 to 17 bin all the way down to the -1 to 1 bin. And looking at our actual data, of course, we can be much more specific. Okay, so that's about all you can see from the histogram itself without knowing more about your data. But that's how you do that. All right, so moving on, if I could get this to close. All right, so we've reviewed how to make a histogram. So now describing shape, look for skew or symmetry. If it's skewed left, that means you have a long tail to the left. Skewed right, long tail to the right. Is the graph unimodal, bimodal, or multimodal? Now be careful about variation, right? Graphs are not going to be perfectly, unimodal all the time. If you have a little tiny dip and then it goes up again, that doesn't necessarily mean it's bimodal. If you believe those two peaks are meaningful, then you might say, I have got a bimodal graph. Okay, a constant graph is flat. That means all the bars are the same height. Or sometimes we call that uniform. Most graphs that are unimodal and symmetric are not normal, so don't say that it is normal in shape unless it really is. You might say it's normal-like or normal, but don't call it normal unless it's truly normal. Okay, be very careful about using that terminology. For outliers, look for gaps, empty bins. Are there values that are unusually far from the rest? We'll be more quantitative about that in the next chapter. For the center, which bin would contain the midpoint or the median? If the data are skewed right, the mean will be above the median. If the data are skewed left, then the mean will be below the median. If the data is symmetric, then the mean will be in about the same place as the median. And we'll be more quantitative about that in the next chapter. And then spread, right now we can talk about range. We're going to be much more descriptive in Chapter 5. We'll be able to talk about standard deviation and interquartile range then. Now, if you're doing socks and you're asked to compare and contrast, be careful not to just do socks for both displays, but to actually take care to truly compare, tell how they are alike, and to truly contrast, tell how they are different, and do that separately, each one for SOCS. So shape, how are they alike or different in shape? How are they alike or different in outliers? How are they alike or different in center? How are they alike or different in spread? Don't leave one out. If there's nothing interesting to say, then say that. So like if there aren't any outliers, don't just pretend like you didn't even think about it. Mention that there aren't any outliers. Okay? Last thing is just, in general, whenever you have data, examine the 5 W's, who, what, when, where, why, how. I know that's not really 5, but they often call them the 5 W's, to see what you really know about the data. So who is not who gathered the data. Who are the subjects the data is about. This might not be people or living things, so you might want to call them what's instead. Okay, but when we're talking about data, that's who the data is about. So if you don't know that, then you don't know hardly anything about the data. What data was gathered? I.e., what are your variables? Are they categorical? Are they quantitative? What units are there? When? This is not when the study was published, but when the data occurred. So sometimes you have to do a little bit of digging to figure that out because it's not always obvious from the information provided. Where is not where the study is published again, but where the data occurred. Why is what is the question the researcher is trying to answer, and how was the data found? Is it an observational study, experiment, sampling, simulation? What is the scope of inference? Are there concerns about design? If you don't have answers to all these questions, you may not be able to make valid conclusions about the study and about the data. And that concludes our review of chapters 2.